I'm going to spend a few slides on who Aeris is, who we are, just in case you're not familiar with us. What we are is a company based in North America and offices around the world. We are a provider of global IoT services. Our headquarters, even though they're located in California, we have operations in California as well as in Chicago, the United Kingdom, India, Japan, and network centers also located around the world. We provide a couple of solutions, which are called the Aeris connectivity platform and the mobility platform, designed from soup to nuts implementation of IoT applications and solutions for our customers. We're completely 100% IoT focused in the markets that we operate and support our customers with our connected cars, fleets, utilities, healthcare, smart cities, financial, industrial IoT, and many, many more applications and devices. If you look in terms of the numbers for representing Aeris, we have had a robust history of growth. We currently offer services, cellular operational connectivity services in about 180 countries. I'll be the first to tell you that not all devices that we have are currently available and used in all those countries, but certainly our connectivity is available and could be used in all of those countries. About 15 million devices on the network today and growing rapidly. We are processing more than 4 billion messages per day on behalf of our customers, and we're currently, in terms of global IoT cellular units, in the top 10 around the world. So with those informational slides about Aeris, let me get started into what blockchain is all about. The elevator speech, and there's sort of 3 bullet points that I can give you which would highlight how and to treat blockchain. Basically, it is a shared, distributed, and very highly secured ledger. The idea is to be able to securely record transactions. Anytime you sell or buy or transact an asset, you provide that asset to somebody, you can record that transaction inside a blockchain. This asset could be tangible property, for example, real estate. It could be houses, it could be vehicles, etc., or intangible information, copyrights, branding of your products, patents that you may have, and now we want to be able to transact of that asset, the patent itself, the contract, and of course IoT, which I have not touched over here, but because this is sort of the elevator speech, it can be applied to anything, not just IoT-related assets. Now, what is a blockchain network? There's a lot of confusion, there's a lot of hype, a lot of things that people don't understand about it. Basically, it is a technology to deal with trust. The idea is that you want to record transactions, and you want to be able to record transactions associated with assets. If an asset moves from one owner to another, tracking that transfer of ownership is something that a blockchain network is ideal for. It is a secure log, it is a distributed log, and it is a shared immutable historical log, meaning that not only do you have access to be able to make changes to the transactions or add transactions to the log, but other people can see it and see pieces of it as appropriate for that particular purpose of recording that transaction. Now, I want to emphasize something very important, and I may say this again later on as well. It is a technology that allows applications like Bitcoin to exist. People sort of mentally assume that all blockchain networks are associated with Bitcoin, which is a cryptocurrency that has been commonly used and sort of very commonly thought of as an example of what can be done with non-material coins. But the fact is that they are not the same. Bitcoin uses blockchain network, and blockchain networks can be used for other purposes. There are multiple implementations available. I recommend very strongly to go to the Linux Foundation and look at the Hyperledger solutions that the alliance that has been formed for implementations of blockchain networks. In particular, and I emphasize this very carefully, what I'm going to be talking about in this presentation has to do with first-generation blockchain and some of the issues associated with blockchain networks that people who are working on next-generation blockchain networks are implementing solutions, if you will, for those issues and concerns that I will talk about with first-gen blockchain. And the Hyperledger Foundation work from the Linux Foundation work is in a place where you can go get more information about next-generation implementations of blockchain. So let's look at some examples of older transaction systems that has served us well over the centuries. Everyone knows about the highly trusted mechanisms like hard coins and paper money, getting letters of credit from banks, and then, of course, the systems for monitoring those transactions when you transfer money from somebody, from one person to another, etc. And then there was a trust transfer. I mean, you can use phones, you can use credit cards, and of course, postal mail, you can send checks. And what's happening today on the internet is the ability to conduct transactions on the internet. What are the issues? Clearly, cash can only be used very locally in small amounts, generally speaking. And the intermediaries, like the banks, are fairly high cost transactors of that information. You can have walled garden systems such as the credit card processing companies that exist today, and all of these transactions and the settlements can take time. That's the issue that traditional older transaction systems had, and the idea was to try and replace that with something that can be more trusted and more electronic. Let's take an example of a traditional business interaction that exists today and how you might implement that in a blockchain kind of solution. Let's say you have a business A and a business B that is implementing a purchase and sale kind of transaction. Business A is selling some products, business B is buying those products, and they each maintain records. They each maintain copies of what's happening, information of transactions that take place. The business A may keep their information in one database, business B keeps it in a different kind of database. Each of them may have unique formats, unique tools, and there's a fair amount of duplication of effective effort, if you will, to maintain that information in two separate systems. Then, of course, there's the auditor and the bank who may be involved in keeping track of those transactions. You may have intermediaries, a bank who transfers the money back and forth through an account that they hold on behalf of business A or business B. You can have delays in the logging and settlement as a result. And clearly, when you have this kind of an arrangement, business A cannot necessarily understand what security the business B might have for maintaining confidentiality and security of the records associated with the transactions. If you want to do electronic transactions, now you need APIs. You need to do formatted data conversions. And because the information may be entirely different in those different records and databases that the companies maintain. So how would you take this traditional business interaction and change it into a blockchain solution? And the idea is that you create a single blockchain network, a ledger that has been well defined for the business that A and B are the business company A and the business organization B are transacting. Those two entities maintain the same information associated with those transactions, but the difference is they do not maintain different copies, different systems, different databases. They're all using the same digitally signed blockchain ledger. In other words, they have access to the information that's appropriate for them to have access to, and they maintain a replica of that entire ledger. So if they make a change on their copy of the ledger, once it's approved by either the bank or the auditor or all four entities involved in this simple model over here, then business B can rely on their replica of that blockchain to be updated automatically. They don't have to worry about sending a query, and you can start seeing where this becomes a very powerful tool for making sure that the transactions occur very rapidly. You don't have to send a query. You don't have to call business A and say, hey, has this transaction cleared for you? You don't have to contact the bank and say, has my account been updated? If the blockchain implementation works properly, exactly the way it's designed, everyone knows what's going on, and everyone has access to the pieces of information that's appropriate for them to have access to. For example, the auditor may have access to the transaction records, but doesn't necessarily have information within that blockchain. You can design the blockchain to prevent them from having access to the banking records that business A and business B might maintain. The point is that all of this effort to look at the same blockchain makes the effort duplication goes down. The duplication of effort goes down. You don't need to have APIs. You're all relying on the same ledger, and you're relying on the fact that the ledgers are properly updated securely, and there's consensus going on to make sure that it's completely valid. The characteristics of any blockchain network are that you must have consensus. For a transaction to be defined as being valid, all the entities necessarily defined as control mechanisms for that blockchain must agree on the validity. And these mechanisms are designed to achieve consensus. You can define that a smaller subset of the entities could be used to achieve consensus. And this is one of the ways that cryptocurrency works in the world today. Regardless, the point is that you have to achieve consensus to make sure a transaction is valid. You can then rely on the fact that the entities can have information about where the assets came from, where the transaction came from, and how the ownership of that asset changes over time. There's provenance, there's historical records that allows you to assure yourself that the information is correct. There's immutability. If you tamper with a transaction, you invalidate it, and that can cause a problem with, for example, recognizing that one transaction is invalid and if it's been tampered with. And the idea is that if you make an erroneous transaction, you can add a transaction later on that reverses that error, as long as you make sure that both are recorded so everyone can agree that the appropriate erroneous transaction has been handled. And obviously, there's local finality. It's a shared ledger. You can determine asset ownership right there and there. Right there, without having to rely on going back and asking the various entities, is this ledger correct and accurate? It's accurate right there because you've maintained a copy, a replica, if you will, of that ledger. Now, and I'm going to use another little interesting example, which I think illustrates a more traditional business model that everyone is familiar with, which is how do you lease a car? The manufacturer manufactures the car. They have a proprietary information about that car. They transfer that ownership of the car to the dealer, who may have their own proprietary ledger and database associated with keeping information about the car, and so on. Leasing company buys the car from the dealer, leases it to somebody, and then, of course, eventually, when that car is reached its useful end of life, it's sent into the junkyard. The problem is that every one of these entities maintains their own copy of the ledger, and a regulator like a DMV, a motor vehicle authority, or a tax authority maintains their own records. And the issues associated with this is, again, classic. You have to take the information, send it across different boundaries from the manufacturer to the dealer, for example. Each of them is storing the information in their own proprietary ledger and having to update it, and things can take time. Regulators in particular are often the last to get information about a transaction that has occurred, and it can take some time for that information about transfer of that asset, the vehicle, moving. Now, if you wanted to implement a blockchain version of this, the idea is that you would have a blockchain that has been set up where the transaction that the manufacturer uses to transfer to the dealer is very clearly identified in their copy of the blockchain, and then the dealer has access to the appropriate information in their replica of the blockchain. Now, obviously, this particular chain is designed so that each entity only has certain pieces of the puzzle. The junkyard who gets a copy of the blockchain doesn't know the price that the dealer might have sold the car to the leasing company. They only get information about maybe the final transaction, and the leasing company sells that vehicle to the junkyard. The point is that you design the chain to allow access to the appropriate information that each entity is allowed to have, but it's all maintained in a single ledger, in a single format that everyone has access to and can rely on their copy of the ledger being accurate and correct in a secure manner. So what is the key business benefits of doing this? Why do people use blockchains? Well, obviously, the first and most clear example of this is that you can reduce the transaction times for the recording of those transactions and reduce the settlement time. You can make the settlement become much faster because you don't have to rely on some authority verifying that the transaction is accurate. If the chain has been designed properly, the existence of the chain and entry in the chain and existence of it, the transaction in the chain, allows you to know that everything has been recorded properly for that transaction to have occurred, and it can be done in real time by you looking at a copy of your own of the ledger, the transaction in the ledger, without having to query the other entities. There's a less oversight required, and these three sub-bullet points give you the cost savings that are essential in a blockchain kind of solution for any of these interactions. Because the blockchain is self-policed. If you have set up the blockchain correctly for a given solution that you're trying to implement, then all the entities that need to know or that need to validate a transaction have taken part in that transaction validation, and everything works correctly without having to have a lot of intermediaries. And again, since you're maintaining a single copy of the same ledger that has been replicated, the duplication of effort to enter the information into multiple databases, multiple accounting systems, multiple ledgers has been removed. Everyone works with the same information, and that makes it simpler to keep information. And of course, because the blockchain has anti-tampering features built in, and in general, for a member-only blockchain, it's been permissioned for certain kinds of access, you're going to get tighter security. You don't have to worry about whether or not the other entity that is participating in a particular transaction system has done the proper security controls within their network, within their servers, within their systems. You can rely on the blockchain providing that security for you. Now, the biggest question that people ask sometimes when I just talk about blockchains, if they're not familiar with what this is all about, is they say, what is a blockchain? Why is it called a blockchain? It's how transactions are stored. Now, when I say stored, it is a software system. It is a ledger that maintains the information associated with the transaction, and it's stored in something called the block. I'll give you a pictorial diagram in a minute, which talks about the content of what that block is in a software context. The blocks contain the time and the sequence of the transaction. So every transaction that occurs in a particular sequence records the time of that transaction, and it's built up in a chain, and the blocks are connected in that chain. Basically, the chain maintains information about the transaction, when it occurred, and it's discrete. It's governed by the rules of the particular network entity. I distinguish public blockchains such as the Bitcoin application from private blockchains where you've defined who the entities are who can get access to that blockchain. So obviously, there are differences between what are called permission blockchains and public blockchains, and I'll sort of touch on that just a little bit as we go further here. Each block contains a digital fingerprint that identifies that block and the timestamps of the valid transactions that are associated within that block. Now, a block could have one transaction located inside of it. It could have more than one transaction located inside of it. It just depends on how the chain is designed. It also contains digital fingerprint, a hash, if you will, of the previous block in the chain. That's how it's linked. That is where the connection from one block occurs to the next. It's the information associated with the previous block. And of course, there may be other hashes of the content of the chain which may be encrypted that allows you to understand how to get access to the information inside that particular block. Now, the block hash and the previous block hash, which I'll show you in a minute, is exactly how it prevents the chain from being tampered with. If someone tries to insert a transaction, an invalid transaction in the middle of the chain, it breaks the chain because the previous and next block hashes break. And so the idea is that you can avoid insertions. And you can also prevent the block from being altered. If someone takes a transaction and alters the content within that particular block, then it again causes the hash to become invalid and subsequent transactions would fail. Essentially, every time you make a change that causes the block to be tampered with, it becomes evident to all of the participating entities, and therefore you can avoid the issues that might occur with transactions being tampered with. It avoids that completely to the point where the participating entities can say, hey, this block has been tampered with, this transaction is not valid, we're not going to allow it to be part of it, we're going to invalidate that particular transaction, and it won't be replicated in the ledger. So if you look at the thoughts that I just described in the previous slide, let's look at exactly what the blockchain structure might look like. Now, this is idealized, obviously. This is not a physical block. It's a structure inside software, implemented in software. And I'm sort of picking right off in the middle of a chain, a hypothetical block number 1001 on the left, block number 1002 in the middle, and the block number 1003 on the right. Now, what you see inside the first block on the left is a hash. That hash is the digital fingerprint of that block. It also maintains a hash of the previous block, okay? That's the next item on the list, and then it has its own transactions. In this particular block, there were 2 transactions recorded. Now, obviously, these numbers are made up for the purposes of this description over here. The point is that everything is maintained in a way that allows you to understand if tampering has occurred. Block 1002 has its own block hash shown in light blue, but it exactly has the previous block's hash stored inside of it, and that is shown in yellow in both these blocks, and then it has its own data for transaction 1 containing its own hash. And of course, the third and final block in this diagram on the right-hand side, you can see it maintains a previous block hash, which is identical to block 1002, and it has its own block hash. No transactions shown in that example because you don't have to have a transaction recorded in the block. It may have been inserted for timestamp purposes, for example. The timestamp itself are not shown in this particular structure. It's just to show you how the links are maintained within the structure, all in software, all done through calculations by the people who have access to that ledger. Now, the content, the transaction 1 and 2, for example, in the left-hand block, may not be accessible by all the entities. The rules associated with the blockchain, which has been designed in place for a particular blockchain, allows you to get access to that. There's encryption and digital keys that are used in particular to gain access to the contents of the block for the purposes of getting the information that's associated with a particular transaction. So this sort of gives you a sort of a very high-level pictorial diagram of the structure of the blockchain and how it maintains information. And as you can see, if I were to take block number 1002 and remove it from the chain, block number 1003 and block number 1001 would disagree in the previous block hash, and it would become pretty clear that it had been tampered, and you could reject that removal of the block 1002, for example. So let's look at the types of blockchain networks. I've sort of alluded to this already. I'm not going to be able to dive into more detail over here on these types of blockchain networks simply because that would be beyond the scope of this webinar. But I'll mention exactly what these are supposed to be. There's a public blockchains which don't have any permission, meaning they're permissionless. They're 100% decentralized. Anyone who can access that has access to the transactions associated with that chain network. Bitcoin, the encrypted blockchain network for Bitcoin, is exactly that. It's permissionless. You have access to the information. Now, you may not be able to insert a transaction because of the rules associated with that particular blockchain network, but the idea is you can have access to the content. And in fact, if you go to the website, you can find out exactly what the current state of the Bitcoin blockchain network is. On the far right, you see the permission blockchains, which are private in general. The idea is that the entities are known. They are not unknown entities. They're well-defined entities based on the design of that particular chain, and you have to have permission to either insert a transaction or to view a particular transaction, etc. The idea is that the entities over there have set up the rules defined for that particular blockchain such that some people can insert, some people can view, and maybe everyone can validate a transaction, or nobody can validate a transaction except a designated authority if you choose to make it that way. In the middle, which is sort of a slightly more uncommon implementation of the public permission, the idea is that you have known entities and unknown entities. Nobody has permission to view unless you're given permission. And of course, to initiate a transaction or to validate a transaction, you have to be assigned permission to be able to do that. This is less common. I think the public permissionless examples of Bitcoin and the private permission examples of specific blockchain networks used for specific purposes are far more common. Now, the entities that are associated with any blockchain network, the roles they play in doing this, there's a number of them. They're the users, the people who have the permission to join the blockchain to add a transaction. They're the regulators. They oversee the transactions that are occurring in that blockchain as it grows. They are the developers. This is the important ones who create the applications that enable user access for a given chain. Obviously, in the case of Bitcoin, it's a very simple example of a blockchain that everyone can access. The developers just set the rules for how you can insert a transaction, and it was one developer who created that, et cetera, all the way down to the certificate authorities who provide the encryption certificates for the data that's in there. There's a term in here which I don't like very much. There's the miners. It's come through from the people who do the validation of the chains and adding the new blocks, for example, of chains that have occurred that are for creating new transactions as opposed to perhaps doing the transactions themselves. It comes more from Bitcoin than anything else. I like the word validators instead, but fine, miners is the more common word used today. And these are the entities and the roles that they play, whether it's a public or a private chain. Now, there are some issues associated with first-generation blockchain that we need to be aware of. First is that it's not yet proven at large scale. The first-generation blockchains that exist, as they are used, as transactions are added, they can grow indefinitely. You're trying to maintain historical records from the beginning of the start of that chain all the way through the current state of the chain. And as a result, as you add that transaction, it continues to grow pretty indefinitely. You can't remove the transaction because that exactly violates the principle of why that blockchain network might exist. You need to be able to make sure it's tamper evident. You can't remove something. You can't insert something in the middle of the chain. You always add to the end. And as a result, things can continue to grow. I like to use the Bitcoin example over here as a blockchain that has grown such rapidity, if you will, and now is becoming literally or more gigabytes. I think it's even larger than that today. The size of the ledger, which has to be sent out to every entity that participates in that, is enormous, and that causes problems because the overhead associated with replicating that ledger can be enormous. You have to store that data, you have to compute on that blockchain, and then of course you need to have high-speed networks to be able to send that chain back and forth. That has become an issue for first-generation blockchain, to which people have been looking at other solutions that I would recommend people go look at the Hyperledger Consortium website. That will give you more information about that. Now, something I want to very clearly identify is that when you have a decentralized and a depersonalized blockchain, the fact that the trust has been sent be unknown does not imply enhanced governance. Very important point to keep in mind is that the rules have to be very clearly defined if you want to make sure that the trust continues to exist. Separate the two. Security of the data versus governance of the rules are two separate things. And of course, as I mentioned earlier, the performance of the more public, larger blockchains that are going on and validating those transactions and achieving a consensus between all the entities associated with that blockchain can take a lot of time. Something very interesting is that blockchain technology is something that there are not enough experts and developers in this field yet, growing but not yet enough yet, where that creating these networks and managing these networks and making sure that the rules are managed properly and the entities have the right permissions, etc., is not perfect yet. It needs assistance, and that's where I think some of the technology and the resources available at the Hyperledger Consortium would be a good place to start with. You have to make sure that the entities, particularly in public blockchains, are equal, and the problem is that they're not. Inequalities between peers is already occurring. In public blockchains in particular, where you have some entities that may have compute resources that are dramatically larger than other entities, and as a result, you cannot have sufficient equality between the peers to do validation of transactions. That's an issue that I think will improve over time, but today that's a significant problem with the first-generation blockchain. First-gen blockchain also has some other issues, in particular having to do with the public blockchains. The idea is that you can have information available to every entity, and what you could have is that if the validators are such that more than 50% of them get controlled by one user or one organization or potentially one government, you can control the validation outcome. That you can have collaboration between those users, those nodes basically, where they can insert invalid transactions into the blockchain. This is called the 51% problem. The idea is that if you set up a rule with public blockchains where 51% of the nodes have to agree to achieve consensus, if you end up with an entity that has control over a large number of the nodes, you can have a validation of the problem. Now, this is not necessarily the case with some of the private chains where the rules are well defined. You could set up rules that say all entities have to agree to a transaction entry in a blockchain, for example, which would allow you to have more control, for example. But that becomes a little bit tricky because you might have a scenario where one entity happens to have a server that is down, and now you can't do transactions because you've got to make sure that all of the entities agree. Well, that's a problem because now you need to make sure that the issues associated with letting that replica of the ledger go out everywhere and update it properly everywhere is managed. So you've got to take care of that. Very important point to keep in mind is that the public and private cryptographic keys that you use for the data inside a chain have to be securely kept. If you keep the keys on an insecure platform, then in theory, a cybercriminal could get a hold of that key, and now they could have access to that blockchain, which is not a good thing. So you want to make sure that you maintain good security policies and practices everywhere else, particularly for the keys on that blockchain. Clearly, you could have vulnerabilities. In fact, there's a report of a Bitcoin mining marketplace that was hacked, and they lost a ton of money of cryptocurrency because their platform wasn't secure. Now, that wasn't a problem with blockchain architecture. It's just because their system wasn't secure, and they allowed a hacker to get in and get control of the keys, and therefore get control of the validation process. Now, should you use a blockchain? Should you use it for an IoT solution? Should you use it for a business purposes? What is the things that are essential for you to understand about the blockchain? There are some questions you need to understand before you decide to use a blockchain. Do you need to manage a contractual relationship of some sort, whether it's a transaction of information, a transaction of a purchase and sale agreement? Is it a contract? Is it a patent information transfer? Do you need to manage some kind of a contractual relationship? Do you track the transactions of some kind, whether it's monetary transactions, whether it's transfer of databases or transfer of some information associated that has a value? Do you need to maintain records over the lifetime of a particular asset? I'm not going to go through every one of these. The idea is that you have questions that you need to address. If you're using a manual system, for example, that allows human beings to perhaps make mistakes, human errors that could occur. Do you have a process that requires you to only work from 8 to 5 because your company is only open 8 to 5 and your employees are only there, that causes delays in the transactions being recorded, etc. The point is that you have a situation where you need to make some decisions as to whether or not you should use a blockchain for that particular purpose or not. It's very important to keep in mind that as long as you have a purpose, if you've got these questions and you can answer yes to any of the questions above and more, yeah, you could have a possible blockchain network solution that you could put in place that would improve the conditions that you have. You could improve the recording of the information. You could maintain lifetime knowledge of an asset transfer and reduce the time it takes to interact between two entities. But you've got to decide if the blockchain is the right solution. It may just be that you've got a simpler solution that works for you, is adequate, and you don't need to worry about a blockchain solution. So the point is that if you answer yes to any of these questions, what you're saying is, I have a possible blockchain network solution, and now you need to design it and understand and see if it makes sense for you to do. So let's talk about the kind of IoT applications that might benefit from a blockchain implementation. I use this as just sort of a few system examples. For example, a connected vehicle function. If you're recording the information associated with over-the-air firmware updates for the vehicle after it's been shipped and the user has it out in the street, you need to be aware of the state of the car's firmware, each piece of the firmware that's in there. Given the number of lines of code the car can have, you need to record when it's been updated, who's updated it, and is there any kind of an interaction between two firmware that may have been designed by different entities that supplied parts for that vehicle. There is an example of where a blockchain network might make sense. Door unlock. You have implemented a connected car function for the user to be able to unlock their car door, and now you need to be able to record that securely, perhaps for legal purposes, because they may come back and say my car was automatically unlocked itself and it got stolen. Well, you need to be able to show that maybe the user pressed that button on their own smartphone controller application for doing that door unlock, and now that transaction was recorded securely, and there's no legal justification for a lawyer to come along and say, hey, you know what, it wasn't the user, it was some malfunction of this connected car application. Recording device maintenance logs is a classic example of where I think that blockchain networks could aid in storing the information associated with the maintenance. For example, a public defibrillator that is used and has been used in a public environment like an airport or a library, and now you want to make sure it's been tested, it's been updated. Recording the use of it in some kind of a log might make sense. Automated fleet tire pressures that are monitor systems that are required by the regulators for the fleet industry, that could be recorded in a blockchain to make sure that you could provably say, yes, we've been taking these recordings, and here they are stored in a secure manner. Supply chain management. When a vendor and a supplier are interacting, to be able to order the equipment, have it delivered, guarantee that it's been delivered, or be able to prove legally that in a secure manner that the transaction has been completed, the delivery has been verified, the payment has been made. All of those things are applications where a blockchain solution could make a lot of sense. Clearly, I want to be careful when I emphasize this, because there are some places in an IoT solution where you may not want to use a blockchain network. So I have a set of do's and don'ts that are very important here for IoT applications. For example, I do say that you should use private and permission blockchains for IoT applications. You've got to worry about the fact that IoT could potentially have a security problem down the road. which could be open for cyber attacks, and you want to make sure that the applications that are in place for the storage of the information associated with the application or the control function from that customer was using that application are stored in a permissioned blockchain, not a public one, a private one. Consider blockchains anywhere you need to worry about authentication and authorization. You want to make sure that you can authorize somebody to use a particular function in the IoT application or access to the IoT data, and maintaining a legally immutable history, legally correct immutable history, provable that is the history of that transaction of that asset is maintained, the data in this particular case is maintained, but might be a very good thing. I do emphasize that if you have non-real-time data transaction recording, yeah, consider using blockchains. But if it's real-time data, you may have an issue with the chain and ultimately grows to a point where the blockchain becomes a difficult thing to maintain. I emphasize the word don't insert all, the phrase don't insert all IoT data into blockchains. That's very important because you may be gathering a ton of data which has nothing to do, no useful history to record, and you want to make sure you only record the very critical functions and the information that you need to share between all the entities who are participating. Because otherwise you may end up in a scenario where you have large storage requirements and compute requirements and connectivity requirements which would be difficult to justify. Very important, if you're encrypting your data, obviously, the integrity of the blockchain, you will have to maintain security of the keys and the key management and all of the other mechanisms that are necessary, traditional security mechanisms that are necessary to maintain security. And obviously, don't forget to look at some of the next generation technologies that are coming along in the blockchain world, because first generation blockchain, I think, is starting to outlive its usefulness, and there are the issues that I talked about, you can reduce them or eliminate them for the next generation deployments. And so go look at the next generation Hyperledger consortium that I mentioned earlier, has information about next generation stuff. So in conclusion, my final slide, before I get to some of the questions that we can take from the audience, blockchain is a good technology. It allows you to record certain kinds of transactions and certain history of the asset tracking purposes, the ownership that you're trying to maintain for that particular asset. Think of it as a tool, basically. It applies to some, but not all problems for recording asset history. There are some transactions that may not belong in a blockchain, some transactions that don't make sense where a manual system might be completely appropriate and sufficient. Don't implement and overcomplicate when you don't need to. Clearly, blockchain has potential well beyond IoT. Anything that involves an exchange of value of an asset that needs to be recorded, that should be maintained for the history of that particular asset, that's where blockchain has potential. Obviously, of that particular asset, that's where blockchain has potential. Obviously, blockchain has some uses in IoT. Just have to make sure that you're not putting it into use in places where you're recording non-essential information, because the chain, the storage, the communication might grow uncontrollably. I would not put in implementation of a blockchain for a remote small sensor on a door, for example. I might do it for a gateway, for the security of that particular gateway, to maintain knowledge about the security of the firmware that's been implemented in a particular gateway, for example. There are some weaknesses. If you don't worry about traditional security of maintaining the keys in a very careful way, you could end up with trouble. You got to be careful about that. And of course, there are some next generation technologies that are being made available for blockchains that are removing some of the first gen problems and concerns that you ought to deal with. So that, in summary, are the sort of the information I'd like to present to all the people who are watching and listening today about blockchains and how they might serve a purpose, not just for IoT, for other businesses. Clearly, it was a very high level discussion over here. Diving into depth on any of these topics is tough to do in the format of a 1 hour presentation or less than a 1 hour presentation in a webinar. If there are questions that people have, I'd like them to put it into the question tabs that people have asked, and to make sure that if they need additional information about blockchains, that they can contact us at a later time, and then we can provide that information as necessary.